Hello, everybody. My name is Vladimir Rodionov, and I am a staff software engineer at Hortonworks. My primary job responsibility is hbase development and hbase support for our customers. Currently, I'm working on two different projects. One of the most important right now is backup and restore functionality for hbase, which we will be releasing in HDP platform 2.5 technical preview. So I welcome everyone just to try it. And the second direction of my involvement is time series database and time series applications on top of hbase. Let's start. How many of you are working currently on the IoT or time series application? How many people? Have you decided yet on the data storage technology? Not yet. What do you consider as alternatives? Do you have a short list?
Well, currently we're a legacy base, so we're using OSI Pi. But I want to move us to something like this.
Okay. Actually, I expected, yes, we have a short list, and number one is Cassandra. Let's let know. Yeah, this presentation, of course, not about the Cassandra. Definitely. And I will try to convince you that hbase is currently probably most viable data store technology for storing large volume of IoT data. So basically, what is the IoT data stream? It's a sequence of data points for many types of applications. In most simplistic cases, it's a just simple triplet, like ID, time, and value. In some other cases, it has some additional attributes, value pairs, name value pairs. Sometimes with location and spatial data, but strictly time series. So that's why when we are talking about the IoT data store and IoT data storage, the number one requirements, of course, it should be good time series database, first of all. Do we have a good time series data store which is open source and commercially supported? What is the answer? Yes, of course. It's hbase. So, of course, it's open source. Of course, it's very scalable, and many customers have deployments well over 1,000 nodes. And I mean, dozens of, maybe hundreds of customers of company I work for have deployments in hundreds servers. So there is no question on scalability. As of course, it's a distributed data store. Of course, it's NoSQL, and it has commercial support from both Hortonworks and Cloudera, at least. But what about temporal feature? Yeah, so we can do temporal feature in hbase as well, but of course, it's not out of box, and it will require some not out of box, and it will require some preparation. So you probably will need to do it yourself. And my goal is for you today is walk through the high-level design decisions which you could actually consider when you will be doing the hbase research. So how to use hbase functionality efficiently to build very efficient time series application, time series data store on top of hbase. There are many different requirements for the time series database, but I will actually enumerate several of them, not all of them, but most important in my opinion. If we consider any time series database and we consider the use cases of how customers or users using this database, that in most cases, I mean in majority of cases, in vast majority of cases, the most important data is the most recent data, most of the time. So the requirements number one for the time series data store is preserving temporal locality of data. And preserving better locality data, of course, because we want to cache this data in memory. And the requirement number two, data store must provide efficient compression, because time series data is well known to be very efficiently, can be very efficiently compressed. Sometimes it's less than 2 bytes per data point. There are some tricky compression schemes which I described in scientific papers. You can find them on the internet. For example, Facebook Gorilla in memory data time series database has very interesting compression scheme, and they can compress data down to 1.5 byte per data point. It's very impressive. What else we actually need from the data store, time series data store? It would be good to have the ability to do automatic time-based roll-up of the data, aggregation, different types of aggregations with different time resolutions. So, because in many situations, in many cases, we are not interested in raw data points, but we're interested in some post-processed data points like aggregated data. Yeah, we would like to have efficient caching policy because we are absolutely sure that this is not only a write-intensive application, but a read-intensive application as well. And having a good caching ability will help us to get the very good read performance in the data store. It would be very nice to have a SQL API access. And of course, we currently were looking on the, is it possible to implement IoT use cases using hbase? Because they're quite specific use cases. This write-read ratio up to 99 to 1, and definitely we're talking about millions of operations per second. Ideal hbase time series database, as we see it right now, keeps raw data points 4 hours. So when we receive raw data points, we don't want to store them forever. The idea is, on the next slide I will show you, is just post-process this raw data, compact and aggregate. That's why we really don't need the raw data, and we don't need raw data to be kept for a long time. And we don't want compact raw data at all. This is actually where I first time mentioned slower compaction. I am not sure that everybody here is familiar with hbase internals, but one of the hbase internal component is responsible for data compactions. Because the hbase writes never overwrites data in place. It uses log structured merge trees approach in the storage system. The data periodically needs to be compacted or merged. So the data needs to be merged from different files to create the single file. This process is called compaction, and during compaction, hbase actually dumps deleted data, dumps expired data, and deletes all the values which exceeds the maximum available maximum version for this particular cell. And compaction in many situations is quite a heavy process. So basically, when we do compaction, compaction can affect the performance and stability of the overall cluster. Instead of keeping the raw data in hbase, we would like to store full resolution data only in compressed form. So we will need compression. And we would like to have different time to live policy for different aggregation resolutions. And if we run compaction, this should be some different compaction algorithm, which actually at least will try to preserve data locality and will try to keep this data in a hbase block cache. And the last in this list, yes, we would like to see the integration with the Phoenix SQL, which is the SQL layer on top of hbase, because we know for sure that customer will appreciate having the SQL interface to access database. Let's talk about the right path for time series database based on top of hbase. This is a very high-level design. It's not the basic design. It's not the basic approach. How many tries to write the application right now? But this is what we will be iteratively discussing during my presentation. So we will return to this slide many times, but with different details. So raw events, they arrive from the left. Region server gets these events and direct them into the raw event column family, which is on top on the right side. Periodically, we have a two coprocessor inside the region server. One coprocessor is responsible for the data compression, and another coprocessor responsible for the data aggregation. Periodically, say one time in hour, we run periodic jobs, which actually reads the most recent raw data, compress it, and aggregate it, and store compressed data in the different column family, and aggregated data in different column families as well. For each type of aggregate resolution, we propose have separate column families. The reason is because we need to have ability to set the different retention policy on the different types of data. For example, we would like to keep raw data for 2 hours, compressed data for 1 month, and aggregated data for 1 year. Yes, because this is a separate column families in hbase. Each column family allows us to set the different time to live parameter on the column family, and that's how we can get this different retention policy for free, basically. Let's go back for a second. Yeah, this is just addition of some additional components which somebody, of course, needs to write, like a compressor and aggregator. But nothing new else. What downside here? The downside is pretty simple. We still using the standard hbase compaction policies, which is the exploring compaction policy in this case. And this compaction policy is well known for very large read-write amplification and a very large load on hbase server. So probably not a good approach. Probably the server will suffer some performance issue. What can we do here? We can change the compaction policy, at least for the raw data. The FAFA compaction has been introduced recently, which actually doesn't do any compactions at all. If you specify FAFA compaction policy for the column family, all the data just will be purged when the data expired. That's it. So there will be no single compaction event on this particular column family. So what it gives us extreme sustain rate. So we can sustain, such column family can sustain hundreds megabytes of second in write operations. And this is what we can use for the raw data set, because raw data set is very short-lived. And even if it's short-lived, without this particular compaction policy, it's still eligible for minor periodic compactions. And with these minor periodic compactions, just adds additional load on the IS system. This particular compaction is already available in all commercial version of hbase, starting with 1917, which is quite old, and all the recent hbase distribution 1.1 and up support this compaction policy. Can we use FIFO compaction for different column families? For example, for compressed data or aggregated data? No, we cannot, definitely, because the retention policy for this type of data is something different. So they probably will live for months, sometimes years, and we cannot afford having thousands of non-compacted files in a file system, definitely. For this type of data, for compressed data and for aggregated data, we can use the standard exploring compaction policy, which is already in hbase, of course. It's a default compaction policy, and add some additional configuration parameters. So by default, exploring compaction is not good, of course, because it doesn't preserve temporal locality of data. It trash block cache a lot. It hurts most recent, most important data access pattern. And no, but if we add some additional configuration parameter, which is the max selection size, we can actually easily simulate what we need, basically. Maximum selection size prevents compactions from compacting size, from creating basically files which is larger than this max size. So if your compaction selection exceeds this max size, these files will not be eligible for compaction. This is basically allows us to get what we want. It allows us to get the recent data points which are close to each other. They, with a high probability, will be kept in a single file. Data points which are pretty far from each other will be kept with a high probability in the different files. So this will allow us to preserve the locality of data and to provide very good read performance in this type of applications. Another alternative to this combination is using the day-tier compaction. It's day-tier compaction policy, yes, already in hbase. It was designed after the well-known Cassandra implementation, specifically for time series. And basically, in a few words, it's just, yes, it collects data in files based on the data age. So the data points approximately of the same age will always be at the same file. Data points from different ages will never be in the same file. Again, this compaction policy works good in applications where the most recent data is most important data. There is one additional feature which unfortunately not in hbase yet, but it exists as a patch. It's called delayed compaction. We can set the delay on the first compaction event, like 24 hours, and it will allow us to keep all the files up to 24, newly created files up to 24 hours without any compactions. And it will allow us, if we don't have compaction events, it means we do not trash block cache, because after compaction finishes, all the old data gets evicted from the block cache. This is called block trashing, basically. And this is what we would like to avoid in many cases. Yes, without block trashing, we definitely get the better read performance. So this can be used, but as I said already, it's just a patch, and it's not in hbase yet. So this is updated schema from the previous slide. So I put the particular compaction policy on the column families we are working on. So the column family with raw data set we will get FIFO All other school family will get either modified exploring compaction policy or date tier compaction policy. So it should be actually fine for both. With the current implementation of a block cache, we have some limitations when we work with the time series databases, time series applications. Current policy is not optimal for time series applications. We need something similar to FIFO. We need support for, of course, very large sizes of the caches. Yes, this everything is work for future, and definitely the corresponding ticket will be opened shortly for the more optimal implementation of the block cache in hbase to support time series application. But currently, what you or we can do to make everything works. It's disable caching for raw data completely because the volume of the raw data set is extreme, and it's just churn data in the block cache and prevents the real data from caching. And enable cache on write and read for compressed data and aggregations. Just two advices. This is what I call the flexible retention policies. So, and they, of course, configurables and or per column family. This is one of the major requests from customers who want to see configurable retention policy for different type of aggregations and for different types of streams. And the second major request, they want to see the compressed data or real compression of the data. What the expected I/O reduction, if we consider the hbase application, which just receive the data points and store them directly in hbase table as read, write, load as 100%, then a combination of FIFO and modified exploring compaction policy will give us approximately 2x reduction. If we add real compaction to the above, so we'll get approximately 10x reduction. 10x reduction is very good because our goal is actually to have a server which can sustain 200K operations per second, 200K data points per second per server. With this type of load, the base application actually will incur 50, 100 megabytes per second sustained rate in the read and write operations to HDFS due to compaction, read-write amplification. And the most optimized version will need only 510 megabytes per second, which is definitely much more reasonable. In the first test we run already, we can see that the combination of all these improvements give us desirable 250K per second sustained rate in a long run. And then this is on a pretty medium server, but SSD backed. So no SSD, not HDD. These are a list of summaries, a list of recommendations for those who would like to start writing time series data store on top of HBase. So we simplify everything. So our goal is to make everything as stable as possible. And the more simple design, the better. What we don't do, we do not run HDFS balancer, because HDFS balancer has no idea about the HBase data actually distribution. And we would like to have the data always locally. We disable HBase outer region balancing as well for the different reason, basically. So we disable region splits completely. If somebody needs to split regions, they can do it manually, not automatically. It's doable, but all the region splits needs to be disabled because region split is the source of in hbase. It's the source of stallness, and the source of compaction storm. It's in the source of higher latencies, and potentially it's the source if we have a storm of region splits. It's the source of system instability. Yeah, you should have the separate column families for raw, compressed, and aggregated data. And of course, you need to increase some configuration parameters, like block and store files for all column families, especially for column families which uses FIFO compaction. Use FIFO for raw data, exploring compaction, tweaked, or DTCP for compressed and aggregated data. Run periodical internal job coprocessor to compress data and produce time-based rollup aggregations. Do not cache raw data, write, read, cache for others. Enable wall compression. This is a must unless you don't do the replication, but it seems that replication works fine with wall compression right now. Wall entries for time series application for data points, they are quite large. And the ratio of the wall size without compression to the data store size is sometimes like 5 to 1, 7 to 1. So with compression, it's close to 1 to 1. And of course, use maximum compression for raw data set, again, to decrease write I/O. What about read path? Although 99% of the operations usually writes, some operations reads. So what we are going to do with the reads? Unfortunately, we still do not have the real integration of SQL and hbase custom data stores. It's kind of tricky, heavy, and it's not feasible. So for those who is going to start immediately to write application, you can do it yourself. Each time series, each IoT stream has a set of attributes, usually, named attributes. It's a pair of name value. So create the special type or meta table in Phoenix where you describe all type of your time series or IoT streams. Keep this meta in Phoenix table. You have the operations to add new time series or delete time series or update time series using the standard SQL shell and to access Phoenix table. Meta is static, mostly. Define set of attributes in meta which creates primary key. Of course, you have to do this because you create the table. Each table must have the primary key. Have primary key translation to unique ID, which you will use in hbase as a time series ID. Store ID, reverse timestamp, and value in hbase. OK, now you can index time series by any attributes in Phoenix. So what will it get you? So let's consider the query flow. But you will need to use, of course, two-step process. So firstly, you access Phoenix to get or select the list of IDs involved. Then you access hbase directly and run query on this ID list. Just suppose there's on the left, this is a meta, right? It's some kind of meta information about the time series we store. And on the right, this is a raw time series data in hbase table. We run the SQL query, where we select IDs from meta where some kind of manufacturer equals SA and version of some device is equal 1.1. So the result of this SQL select is some ID set. Then next step, we will use the API to access hbase directly and get this ID set and run some kind of aggregation function, which you, of course, will need to implement yourself. This is how you can combine both without very complex, actually, I would say, development. What about the time series database API? What you will need to implement at the minimum. So, of course, you will need to implement group operations on ID sets by time range, like min, max, average, count, sum, and other aggregations have pluggable aggregation functions. Support for different time resolutions and with different approximations, linear, cubic, bicubic. Batch load support, of course, for writes. And this can be implemented in hbase as a coprocessor layer. And of course, it can work much, much faster than any regular SQL database because we have already aggregated data in a table. And for many types of queries, the response is going to be immediate. Thank you. That's what the last slide. So if you have any questions, we have 6 minutes.